Hello everyone, I'm Leonardo, and today I'll be talking about gray box Bayesian optimization in function spaces using NEON, which stands for Neural Epistemic Operator Network. This talk is going to be based on the paper that I'm showing over here, which was co-authored by me and my advisor, Perdikaris. You can learn more about it by checking the QR code or the link over here in the screen. This paper largely talks about AI-accelerated engineering design, where we have a certain design space that we want to explore specifically to find the design that optimizes some hard-to-compute function. We start with this design space and with an initial set of designs for which we've carried out experiments. In here, the x's represent different designs, and the y's represent the objective value, how good this design is. Generally, under this framework, you would then fit a probabilistic model, also called a surrogate model, to fit this data. In particular, we want a model not only that gives us a specific prediction, but that also quantifies uncertainty, that gives us a notion of how sure it is of this prediction. We then use this surrogate model to compute an acquisition function that captures some notion of how useful it would be to build this experiment, build this design, and test what its objective value is. This acquisition function generally tries to balance the exploration and exploitation of the problem. Finally, we maximize this acquisition function to determine the next design to test. We test it, collect this data, add it to our set of designs that we've have experimented with, and rinse and repeat this cycle until we have reached something that's satisfactory. So in the remainder of the presentation, I'm going to talk about the two main contributions of the paper, namely the Leaky Expected Improvement acquisition function and the Neural Epistemic Operator, or NEON, architecture. I'll start with the Leaky EI. So one of the most popular acquisition functions used in Bayesian optimization is the expected improvement, where, as the name suggests, it computes the expected improvement over the best value we have observed so far in our experiments. In here, y star is the best value we have found so far, and it can be formulated in this way over here, and it can even be framed in terms of this ReLU function that is well known from the machine learning community, the rectified linear unit. This acquisition function is very successful, but it does have some problems. In particular, it's very hard to optimize because depending on the problem, the gradients of this function with respect to the input x is going to be 0 for the vast majority of inputs, especially as y star, the best value so far, increases. This is even more drastic of a case when we look at cases where x is high dimensional. So this largely is the problem of vanishing gradients that has been addressed by some other methodologies in deep neural networks. In particular, we had the idea of replacing this ReLU within this acquisition function with leaky ReLU, making it very similar to traditional expected improvement, but with a key difference that now the gradients with respect to the input are no longer going to be 0 for the vast majority of inputs, which makes it amiable for gradient-based optimization. We call this acquisition function the Leaky Expected Improvement, or LEI. And let me show you an example of what this looks like. So over here, we have a toy example that we have some data, and we have a mean prediction, and you can see here different samples from a surrogate model. And in the bottom over here, I'm plotting both the value of both the expected improvement and the leaky expected improvement. You can see when we don't have a lot of data, they generally perform very, very similarly. There's a little bit of a difference, but generally, whatever point optimizes expected improvement is also going to optimize leaky expected improvement, and vice versa. No matter where you start your optimization process over here, if you run gradient descent, you're going to converge at least to a local optimum. However, once you start collecting a little bit more data, maybe the predictions and the acquisition values start looking something like this. You can see over here on the left, we have a large section over here where the expected improvement is exactly 0. There's no gradient to be gotten over there. But if you fall within one of this other side of the graph over here, then you actually can run gradient-based optimization and you're going to converge to one of these local minima that is going to be useful for your problem. Already here, you can see that if you start over here, the leaky expected improvement is going to have small gradients, but there's going to be some gradients that make you converge either over here to the right or to the left. Now, once you start collecting more and more points, the probability that you actually surpass the best value observed so far gets very, very low. And in particular, a lot of cases, particularly in high dimensions, look a lot like this, where there are only gradients in a very small section of the input space. If you initialize your point somewhere over here in run gradient optimization, you will find this local optimum over here. But if you start anywhere else and use expected improvement, the gradients are going to be exactly zero, and you're not going to be able to iterate it at all. However, once we use the leaky expected improvement, you can see that there are gradients to latch onto, and generally speaking, flowing the gradient is going to give you some useful information. If you start over here, you're going to converge to the global optimum, and for example, even if you start over here, you might converge to this point over here, which is a local but not global optimum, but still captures some more information that is useful for your problem. In here, you can see that you would collect a point over where we have a lot of uncertainty. So in this case, leaky EI is a cheap, simple alternative to expected improvement that is much easier to optimize via gradient-based methods. So if you've heard about this problem before, you may be wondering to yourself, what about the log expected improvement? This is another acquisition function from this paper, an expected improvements to expected improvement, that was authored by some researchers at Meta's adaptive experimentation team. And they also address largely the same problem. These both works were done around the same time. And they both try to address this problem that expected improvement in practice is hard to optimize. And in their paper, they propose a different variant that is very similar in flavor, but uses more of a fat soft plus function instead of leaky value. And there's also some differences in the parallel acquisition setting, but I highly encourage you to check out their paper. There's also a lot of very interesting analysis over there. Now, moving on to the second part of this talk, I'll be talking about neural epistemic operator networks, or NEON for short. So, our paper revolved largely about composite Bayesian optimization, or gray box optimization, which is the following setting. We, as before, have our set of potential designs over here on the left, and we have some unknown objective function that gives us a scalar value that we want to optimize. However, in composite Bayesian optimization, we also know something more about the structure of this problem. We know that f is the composition of an unknown function h with a known function g over here. So for example, let's suppose that we have cell towers spread throughout a city, and we want to optimize the signal the transmission strength of each tower and also the antenna angle so that we want to maximize the cellular service in the area while minimizing interference between the towers. Over here, going from the set of initial designs, which is the antenna's intensity and angle, to this map where we have the strength and interference across the entire city is a very hard to compute function. But once we have these two quantities over here, it is actually very easy to compute the objective value that we care about. We can just look at the matrix and see what are the areas that we don't have service or that we do have service, but the antennas are interfering with each other. And using this information encodes useful information about f. We kind of replace this black box nature of f with more of a gray box. We still don't know everything about it, but we're leveraging more information of this intermediate space. We are leveraging information about this composition. And in particular, we observed cases where this intermediate space is a space of functions. So over here, I have a Venn diagram showing that Bayesian optimization as this larger sphere, and composite Bayesian optimization as a subset of Bayesian optimization. And finally, we have operator composite Bayesian optimization as a subset of this, where the intermediate space Y is a space of functions. Over here, for example, the space of continuous functions from Y to some output space R ds. In particular, if you see over here, this example shows a function space that is the space of continuous functions from R2 to R2. The input spaces are 2 because we have over here a map that is in 2 dimensions, and the output spaces also are 2 because we predict 2 quantities, the signal strength and the interference. And this makes this problem fall under the realm of operator learning, which is a very important paradigm in science and engineering. In operator learning, we're trying to do machine learning, particularly often deep learning, where our inputs or outputs are no longer just finite dimensional vectors, but rather potentially infinite dimensional function spaces. And this is a very active field nowadays with a lot of really interesting research coming out every year. Before I move on and actually describe the Neon architecture, first I want to talk about epistemic neural networks, which is a theoretical framework from this paper by Ian Osmond that is really useful to quantify a lot of like common methods for uncertainty quantification in deep learning. The basic idea of an epistemic neural network is that it's any model that takes as input an input variable x, which is what we actually care about, and an epistemic variable z. In this case, z doesn't have any connection to the data and is just generated randomly at every time we want to make a prediction. Then the ENN takes these two values and carries out a prediction. So let's look at an example. Let's say we want to classify different images, and you can see here x, or input variable, may be the image of this Siberian tiger, and the z, the epistemic variable, may just be a random vector in 2 dimensions over here. And passing this over to our epistemic neural network, we have a prediction. It's a Siberian tiger. Maybe we change the epistemic variable and predict again, and the prediction is still Siberian tiger. Now let's say we change it once again, and the prediction is still Siberian tiger, which makes sense because this vector over here has no connection to the image at all. However, let's say now that we have this image of a capybara. Maybe given a certain epistemic variable, we have that the prediction is capybara. That's great. But let's say that we change the epistemic variable, and now we have the prediction of a beaver. And then we change again, and it tells us that it's a Siberian tiger. So something's going on over here. In the first case, the predictions did not depend on the epistemic variable, but for this image, they do. This tells us something very interesting. It tells us that on the left, this image has low epistemic uncertainty, whereas on the right, they have high epistemic uncertainty. Epistemic uncertainty here meaning the uncertainty that we have regarding lack of data. What this means in practice is that the model has seen a lot of images, for example, of Siberian tigers, and then it's fairly confident of the output should be Siberian tiger. Whereas on the right, it just tells us that depending on this random variable that we feed to the network, it's going to give us different predictions. That means there's high epistemic uncertainty. And in particular, this tells us that exploration should prioritize the picture on the right. And we can make this assessment without ever really needing to know the true label of each image. We just know that on the left, one of them depends on the epistemic, and one of them does not depend on the epistemic in this, and on the right, it does. And this framework of epistemic neural networks actually fits a lot of popular neural network architectures, in particular deep ensembles or Bayesian neural networks, and so forth, and even, for example, Monte Carlo dropout. And so the idea for Neon is to use one particular type of this epistemic network that's called an EpiNet. So Neon, as I'm showing over here, has 2 basic components. We have a base network that takes as input the things that you actually care about for your problem, in this case, U and Y, and outputs mean prediction mu over here. This base network is considered to be large and can be very powerful. From this base network, we also extract a set of features x tilde that are, for example, a concatenation of the inputs with maybe the last layer of activations before the output. And we also carry on this stop gradient operation over here. This set of features x tilde is passed to the EpiNet along with this epistemic index z that is going to change at every iteration to predict to give an output value sigma over here. And then we add these two components over here to give our final prediction f theta. Now, the Bayes network can have many different architectures. In particular, the ones we use in this paper kind of follow this encoder-decoder architecture, where we have some encoder, and then we pass it that encodes the input function u, and then we have our query location y gets passed to Fourier features, and then these both quantities are passed to a decoder that outputs the mean prediction mu. On the other side, the EpiNet, which is generally speaking a much smaller network, has also two components. It has a learnable EpiNet and a prior EpiNet. In this case, the prior component is initialized at random and is never changed during training, whereas the learnable EpiNet is trained. And the effect that this has is that effectively, assuming the Bayes network is properly trained, the learnable EpiNet has to learn to counteract the effect of the prior EpiNet over here. So it will be able to do that in regions where it has seen data x tilde, and it will not be able to do that in regions where it hasn't. And this allows us to effectively capture the epistemic uncertainty of our problem. And there's more analysis in the paper that you can read about, and also in that work I mentioned previously, the Epistemic Neural Networks by Yoon Osmond and company, has some really interesting analysis of why this strategy works. And so we actually went on and tried to evaluate this type of methodology for problems in composite Bayesian optimization, particularly in this operator learning setting. And what we found is that compared to other results that were published in the literature, so not even results that we ran ourselves, but just looking at what was published in other papers in recent years, we found that our method generally works very well, better than Gaussian processes and ensembles of depot nets, while requiring significantly less parameters. Over here, you can see two benchmarks, and on the x-axis, we have the number of points that were collected, and on the y-axis, the objective we're trying to capture. And in here, lower is better. So you can see the dashed line, the solid line over here for the neon generally works very well and can converge to a value at either similar or faster than competing methods. And in particular, if you see here the parameter count for the different comparing our method to a depot net ensemble, we can see that we can do it often with 40 times less parameters. And I'll talk a little bit about that in a second, why this is so important. In particular, we also tested this, we had really great results for this problem that is very high dimensional, where we're trying to align two Mach-Zehnder interferometers. So in this case, the intermediate space that we're talking about is the space of functions from R2 to R16, because we have these 16 images over here, and we're trying to basically align them based on a certain objective function, G. This code for this is available on this InterferBot GitHub repository if you're interested in looking at it. And for this problem, that is the highest dimensional problem that we considered, that's where we see neon working the best. In particular, over here, you can see that our method not only is able to start in this case, higher is better. Not only can it start increasing the visibility, it can do so very reliably. In particular, you can see that 1 is the physical maximum for this acquisition function. You can never do better than 1. And we very reliably, across different seeds and initializations, are able to find this. Whereas Gaussian processes generally struggle a lot and depot net, an ensemble of depot nets, for example, also has a lot more variability and take longer to achieve these high objective values. And in general, there's a trend that we found across all of our experiments. Random works, just a random acquisition, collecting points randomly, works the worst, whereas Gaussian processes don't work super well. An ensemble of deep neural networks works a little better, but with Neon, we're able to get even better results. And I think something that's really important here is trying to determine what is the best method to use for each problem. And in my opinion, this flowchart represents a good guideline. So when you're trying to decide what method to use for a surrogate model in Bayesian optimization or composite Bayesian optimization, you should ask yourself, does the problem I'm looking at require or benefit from deep learning? If the answer is no, if your problem is simple or like low dimensional, you should probably stick with Gaussian processes. There's a lot of like good theoretical results, and they generally are true and tested methodology. However, if you do need to use deep learning, you should ask yourself, is there a network already pre-trained on this task? If the answer is yes, I'd argue that you should try to use EpiNets because an EpiNet in this case can be trained after the base network has been trained. So if you already have a very powerful neural network that was trained on this particular task and you don't want to train a deep ensemble, you should use EpiNets because for a very small computational cost, you can go and get uncertainty quantification for the problem that you care. And this EpiNet is also going to leverage a lot of the learned information from the base network. Now, if you don't have a powerful neural network already trained on that task, you should ask yourself, do you have the computational budget to train dozens of models with sufficient capacity, meaning dozens of models that are large enough to capture the problem at hand? If you do have the computational budget to train a large ensemble, I would argue that doing ensemble methods or Bayesian neural networks is probably the best way to go because the uncertainty estimates given by these methods are probably a little more reliable. However, in many realistic cases, if you want to train a neural network on a problem, and you will need to do it using large ensembles. Each ensemble member is going to have to be very small, which means that they're not going to be big enough to really capture the problem at hand. They're going to struggle. So if you can, or if you do require large models to model the task at hand, and you don't have the budget to train a large ensemble, I would argue that EpiNets, once again, are the best way to go. Um, and yeah, thank you so much for sticking around for this presentation. Feel free to send me a message in this email if you have any questions. I'm listing here also some supporting organizations for this work and for presenting at the SIAM CSC conference. And you can learn more about this work over here. In particular, I'm linking the paper, the GitHub repository, and also my Google Scholar page if you're interested in learning some more about my work. Thank you so much.